Welcome you all to the video lecture on transmission lines and RF system. Let's see about the second module of Unit 1 Transmission Line Theory. I am Dr. K. Padmapriya, Assistant Professor, EC Department, Government College of Engineering, Bodi Nayakanur. So in the second module, we can see about the distortionless line. It is desirable, however, to know the condition on the line parameters that allows the propagation without a distortion. The lines having parameters satisfy this condition is termed as a distortionless line. This condition for a distortionless line was first investigated by Oliver Heaviside. Distortionless line condition can help in designing new lines or modifying the old ones to minimize the distortion. A line which has neither frequency distortion nor phase distortion is called a distortionless line. So condition for the distortionless line is RC equals LG. Also, the attenuation constant should be made independent of frequency, that's alpha should be equal to R into G. The phase constant should be made dependent of frequency, where beta equals omega LC. The velocity of propagation is independent of frequency, V equals 1 by LC. For the telephone cable to be the distortionless line, the inductance value should be increased by placing lumped inductors along the line. So for a perfect line, the resistance and the leakage conductance value were neglected. The conditions for a perfect line are R equals G equals 0. Smooth line is one in which the load is terminated by its characteristic impedance, and no reflections occur in such a time. It is also called as flat line. In the distortionless line, if a line is to have neither frequency nor delay distortion, then attenuation constant and velocity of propagation cannot be function of frequency. Then the phase constant be a direct function of frequency. Thus the beta equals square root of omega square LC minus RG plus square root of Rg minus omega square Lc plus omega square Lg plus Cr divided by 2. If the term under the second radical be reduced to equal Rg plus omega square Lc the whole square, then the required condition for beta is obtained. So expanding the term under the internal radical and forcing the equality will give the following relation, which will be reduced to 2 omega square Lc Rg plus omega square L square G square plus omega square Cr square equals 0, which will further lead to Lg minus Cr the whole square is equal to 0. Therefore, the condition that will make a phase constant a direct form is Lg equals Cr. So, rearrange the equation. Lg minus Cr the whole square will be giving Lg equals Cr. A hypothetical line might be built to fulfill this condition. The line would then have a value of beta obtained by the use of above the equation. Already we know that the formula for the phase constant beta is equal to omega Lc. Then the velocity of propagation will be V equals 1 by Lc. This is the same for all the frequencies, thus eliminating the delay distortion. May be made independent of frequency if the term under the internal radical is forced to reduce to Rg plus omega Lc the whole square. The analysis show that the condition for the distortionless line Lg is equal to Cr, which will produce the desired result, so that it is possible to make attenuation constant and velocity independent of frequency simultaneously. Applying the condition Lg equals Rc to the expression for the attenuation gives alpha equals Rg. This is the independent of frequency, thus eliminating the frequency distortion on a line. To achieve Lg equals Cr, it requires a very large value of L since G is small. If G is intentionally increased, then attenuation is also increased, so which will result in poor line efficiency. So to reduce R raises the size and the cost of the conductors above the economic limits so that the hypothetical results cannot be achieved. Propagation constant is as the natural algorithm of the ratio of the sending end current or voltage to the receiving end current or voltage of the line. It gives the manner in the wave is propagated along a line and specifies the variation of voltage and current in the line as a function of distance. So, propagation constant is a complex quantity and is expressed as gamma equals alpha plus j beta. The real part is called the attenuation constant, whereas the imaginary part of the propagation constant is called the phase constant. Next, we can see about the loading and different methods of loading. So, in ordinary telephone cables, the wires are insulated with paper and twisted in pairs. Therefore, there will not be any flux linkage between the wires, which will result in negligible inductance and conductance. If this is the case, there occurs frequency and phase distortion in the line. Quarter wavelength. For the case where the length of the line is 1 quarter wavelength long or an odd multiple of a quarter wavelength long, the input impedance becomes Zin equals Z0 square by ZL. In case of a matched load, it's in another special case where the load impedance is equal to the characteristic impedance of the line, in which case the impedance reduces to the characteristic impedance. Therefore, Zin will be equal to ZL, which is again equal to Z0 for all the length L and lambda. Next is about the short load. So, for the case of a shorter load, ZL will be equal to 0. Therefore, the input impedance is purely imaginary and a periodic function of position and wavelength. So, Zn of L will be equal to JZ0 tan beta L. For open load, ZL will be equal to infinity. Therefore, the input impedance is again imaginary and it's a periodic function of position and wavelength. So, Zn of L will be equal to minus JZ0 cot beta L. When the line is not terminated in Z0, so what else happens? The insertion loss of a line or a network is defined as the number of neppers or decibels by which the current in the load is changed by the insertion. So, insertion loss will be equal to the current flowing in the load without insertion of the network current to the current flowing in the load with insertion of the network. So, this ratio is called as the insertion loss. So, coaxial cable, the coaxial lines confine the electromagnetic wave to the area inside the cable between the center conductor and the shield. The transmission of energy in the line occurs totally through the dielectric inside the cable between these conductors. The coaxial lines can therefore be bent and twisted without the negative effects, and they can be strapped to conductive supports without inducing unwanted currents in them. In RF applications up to few gigahertz, the wave propagates in the transverse electric and magnetic mode. That is, both transverse electric and magnetic means electric and magnetic field will be perpendicular to the direction of the propagation, and the electrical field will always be radial and the magnetic field is circumferential. However, at frequencies for which the wavelength is significantly shorter, the circumference of the cable, the transverse electric and transverse magnetic waveguide modes can also propagate. When more than one mode can exist, the bends and other irregularities in the cable geometry can cause the power to be transferred from one mode to another. The most common use for coaxial cable is for television and other signals with bandwidth of multiple gigahertz. In the middle 20th century, they carried long distance telephone connections. Microstrip. A microstrip circuit uses a thin flat conductor which is parallel to a ground plane. The microstrip can be made by having a strip of copper on one side of a printed circuit, this is a PCB, or a ceramic substrate, while the other side is continuous ground plane. The width of the strip The thickness of the insulating layer, either it may be PCB or ceramic, and the dielectric constant of the insulating layer determine the characteristic impedance. So the microstrip is an open structure, whereas coaxial cable is a closed structure. So in microstrips, it mostly depends on the substrate what it is made, and the strip, the size and the shape of the strip, copper strip which will be placed over the substrate is much important. Balanced lines. A balanced line is a balanced line, excuse me. A balanced line is a transmission line consisting of two conductors of same type and equal impedance to ground and other circuits. There are many formats of balanced lines. Among the common are twisted pair and star paired and twin lead. The twisted pairs are used for terrestrial telephone communications, and in such cables, many pairs are grouped together in a single cable. So, from 2 to several thousands will be present in a single cable. The format is also used for data network distribution inside the buildings, but in this case, the cable used is more expensive with much tighter controlled parameters, and either 2 or 4 pairs per cable will be there. Single wire line. Unbalanced lines were formerly much used for telegraph transmission, but this form of communication has now fallen into disuse. The cables are similar to twisted pairs in that many cores are bundled into same cable, but only one conductor is provided per circuit, and there is no twisting. All the circuits on the same route is a common path for the return currents. There is a power transmission version of single wire earth return in use in many locations. Waveguides. Waveguides are rectangular or circular metallic tubes inside which an electromagnetic wave is propagated and it is confined by the tube. And the waveguides are not capable of transmitting the transverse electromagnetic mode found in the copper lines, and it must use some other mode. Consequently, they cannot be directly connected to a cable, and a mechanism for launching the waveguide mode must be provided at the interface. Reflection coefficient. It's used in physics and electrical engineering when wave propagation in a medium containing discontinuities is considered. So the reflection coefficient, it describes either the amplitude or the intensity of the reflected wave relative to an incident wave. The reflection coefficient is closely related to the transmission coefficient. Reflection occurs because of the following cases: when the load end is open circuited, when the load end is short circuited, when the line is not terminated in its characteristic impedance. When the line is either open or short circuited, then there is not resistance at the receiving end to absorb all the power transmitted from the source end. Hence, all the power incident on the load gets completely reflected back to the source, causing reflections in the line. When the line is terminated in its characteristic impedance, the load will absorb some power and some will be reflected back, thus producing the reflections. The reflection coefficient can be defined as the ratio of the reflected voltage to the incident voltage at the receiving end of the line. And reflection coefficient K is equal to reflected voltage at load divided by the incident voltage at the load. So K equals VR by VI. In telecommunications, the reflection coefficient is the ratio of the amplitude of the reflected wave to the amplitude of the incident wave. In particular, at a discontinuity in a transmission line, it is the complex ratio of the electric field strength of the reflected wave, it's E minus, to that of the incident wave, E plus. This is typically represented with a gamma and can be written as gamma equals E minus divided by E plus. The reflection coefficient may also be established using other field or circuit quantities. The reflection coefficient can be given by the equations below, where the ZS is the impedance towards the source and ZL is the impedance towards the load. So in the diagram you can see the gamma to be marked from the ratio that is nearby the receiving end. Simple circuit configuration, it shows the measurement location of this reflection coefficient. So near to the load. So gamma equals ZL minus ZS divided by ZL plus ZS. So negative reflection coefficient means that the reflected wave receives a 180 degree or a pi phase shift. The absolute magnitude designated by the vertical bars, and the absolute magnitude of the reflection coefficient can be calculated from the standing wave ratio. So modulus gamma equals SWR minus 1 divided by SWR plus 1, where SWR is the standing wave ratio. Let's see about the calculation of current, voltage and the power delivered, and how about the efficiency of transmission. So voltage and current ratios. So in order to simplify the calculations, sinusoidal voltage and current waves are commonly represented as complex valued functions of time denoted as V and I. So V cap equals V naught e power j omega t plus phi V. I cap equals I naught e power j omega t plus phi I. The impedance is defined as the ratio of these quantities. So Z cap equals V cap by I cap. Substituting these into Ohm's law, that is V equals I into R. So we substitute both the values of V cap and I cap there, and we get the simplified expression as I naught into Z e power j omega t plus phi I plus theta. So noting that this must hold for all t, we may equate the magnitudes and phases. So V naught, when you equate the magnitudes, your V naught will be equal to I naught into Z, and when you take the phase component, your phi V equals phi suffix V is equal to phi suffix I plus theta. So the magnitude equation is the familiar Ohm's law itself, which will be applied to the voltage and current amplitudes, whereas the second phase equation, it will define the phase relationship between the values. So power quantities. When referring to the measurements of power or intensity, a ratio can be expressed in decibels by evaluating 10 times the base 10 logarithm of the ratio of the measured quantity to the reference level. Thus, if the capital L, it represents the ratio of a power value P1 to another power value P0, then L dB represents the ratio expressed in decibels. So L dB equals 10 log 10 P1 by P0. P1 and P0 must have the same dimension. They must measure the same type of quantity and the same units before calculating the ratio. So only then you can take out the dB value, the ratio of it, with uniform dimensions. So bell will be equal to 10 decibels. Therefore, the corresponding formula for measurements in bells are LB equals log 10 P1 by P0, whereas P1, rearranging that is P1 is equal to 10 power LB P0. Input and transfer impedance. So if the load impedance is not equal to the source impedance, then all the power that are transmitted from the source will not reach the load, and hence some power is wasted. This is represented as impedance mismatch condition. So for the proper maximum power transfer, the impedances in the sending and receiving end are matched. This is called impedance matching. So consider a stepped transmission line which consists of 3 segments, and the input impedance ZS and the load on the other end. Each segment is of having length L1, L2 and L3, and the corresponding impedances also. It is used for broad range impedance matching. It can be considered as a multiple transmission line segments connected in series with the characteristic impedance of each individual element to be Z0, I. And the input impedance can be obtained from the successive application of the chain relation. So Z I minus 1 will be equal to Z naught comma I into Zi plus Jz naught I tan beta I Li in the numerator, and in the denominator Z naught comma I plus Jz I tan beta I Li, where beta I is the wave number of the ith transmission line segment and Li is the length of this particular ith segment. Zi is the front end impedance that loads the ith segment. The impedance transformation circle along a transmission line whose characteristic impedance Z0 I is smaller than that of the input cable Z0. Conversely, if Z0 comma I is more than Z0, the impedance curve should be off-centered towards the plus x-axis. So here you can see the off-centered, and as a result the impedance curve is off-centered towards the minus x-axis. So because the characteristic impedance of each transmission line segment Z0 comma I is often different from that of the input cable Z0. So each time when it changes from the Z0, it will be moving in both direction, that is it will be off-centered from either to the plus x-axis or to the negative axis. So it will be off-centered along the x-axis of the Smith chart, whose impedance representation is usually normalized against the Z0. Now let's see about open and short circuited lines. So as limited cases, it is convenient to consider the lines terminated in open circuit or short circuit, that is with ZR equals infinity or ZR equals 0. The input impedance of a line of length L for the short circuit case is ZR equals 0, so that ZS equal to Z0 tan H gamma L. The input impedance of the open circuited line of length L with ZR equals infinity is ZOC equals Z0 cot HL. So both of this short circuited impedance and open circuited impedance, you multiply both and you will get the Z0 is equal to ZOC into ZSC. This is the same result as was obtained from a lumped network. The above equation supplies a very valuable means of experimentally determining the value of Z0 of a line. So also from this same two equations, what we get is tan H gamma L equals square root of ZSC divided by ZOC, and gamma dash will be equal to tan, that is gamma L, it will be equal to tan H inverse of square root of ZSC by ZOC. So from this equation you can find that tan HL is equal to tan H of tan H gamma L is equal to tan H of alpha plus J beta L, which is again equated to U plus JV. So from rearranging it and everything, we get the final equation. The value of beta will always be uncertain as to quadrant, and its proper value may be selected if it is velocity of propagation is 0.3333. Reflection factor and reflection loss. The reflection loss is defined as the number of nepers or decibels by which the current in the load under image matched condition would exceed the current actually flowing in the load. So reflection loss in nepers is equal to ln modulus Z1 plus Z2 divided by 2 into square root of Z1 into Z2. Reflection loss in dBs will be equal to 20 log modulus of Z1 plus Z2 divided by 2 into square root of Z1 Z2. So reflection factor denoted by K, it indicates the change in current in the load due to reflection at the mismatched condition and is called the reflection factor. So K is equal to modulus of 2 into square root of Z1 and Z2 divided by modulus of Z1 plus Z2. Insertion loss of a line or a network, it is defined as the number of nepers or decibels by which the current in the load is changed by the insertion. Thank you.